So the dividing collection devices include surface filters, depth filters, and scrubbers, and we'll be talking about each one of them. For the surface filter, the mechanism is that particles are captured on the surface of the filter media. It's used mainly in baghouse and in less extent in something called cartridge filter. This is how exactly your vacuum cleaner works at home when you clean the floor. This is the exact concept of a surface filter. A depth filter is when particles are captured within the filter media. This is used for fine particles and aerosols. And finally, scrubbers are uses liquid to capture particles and is effective for both particles and gases. So in this video, we'll continue with the surface filters. Surface filters collect particles on the outer layer of a membrane, forming a layer or cake that traps finer particles, and it's common in industrial air pollution control for capturing dust and particulate material. See this picture over here. You can see this black now dots that I am pointing them up in red. These are particulates that are collected on the surface of the surface collection. And you can see also the other ones, they are bigger particles that's also collected on it. While they are being collected, they actually form a layer, what we call a filter cake. Just keep in mind that once this starts, it's actually not very efficient. If you have a very clean bag for collection, the bag is actually not very efficient. When does it become efficient? When it starts to collect a lot of dust on the surface. The more dust it collects on the surface, actually becomes much more difficult for any particulate to go through the bag, because it has not only the filter medium, which is here, not only the filter medium to go through, however, it has also to go through the filter cake layer, delta X. Delta X will be the filter cake layer. Now the fluid flow is going from the left to the right here and going out as clean gas, removing behind this layer. So the key components of a surface filter include the filter medium, which is usually a cloth, wire mesh, or a porous material. Cake formation, collected particles create a secondary flotation layer that improves efficiency. Finally, permeability, the ease with which gas flows through the filter depends on the cake thickness and medium properties. So a very important thing you can think of is the pressure drop. And we can all, if you have ever used your vacuum cleaner at home, you will understand what pressure drop means. If your bag is full, it's very hard for the vacuum cleaner to suck more air. It becomes very loud and it's trying to get things across, but it cannot. And this is because it's building pressure across its filter. Once the pressure is too much, it's very hard for the air to go through. And the difference in pressure is what we call the pressure drop. So the pressure drop, here is how to calculate it across the filter. We can start with Vs, which is the superficial velocity. So Vs is equal to Q over A. Q is the flow and A is the area, which is equal to negative delta P, which is the pressure drop, over mu times K over delta X, where K is the permeability and delta X is the thickness of the filter layer. So applying this formula, we can either write it one time for the cake and one time for the filter medium. So if we apply it for the cake, then this will be the delta P. This will be the delta P for the cake, or it can be the delta P for the filter medium. So delta P, which is P1 minus P2 over mu. Okay, go back here. This will be P1, P2, and P3. So if we're talking here about delta P, that will be the difference between P1 and P2, and there is another delta P here, which is the difference between P2 and P3. So P1 minus P2 over mu times K over delta X cake is equal to P2 minus P3 over mu K delta X, that's filter material. So we can rewrite that as Vs is equal to P1 minus P3 over mu delta X over K cake plus delta X over K filter material, which is equal to Q over A filter. Delta X cake will be equal to mass of cake over area times 1 over rho cake, which is equal to 1 over rho cake times volume of gas over area times mass of solids removed over volume of gas. The W collection, which is volume of cake per volume of gas processed, is equal to 1 over rho cake times mass of solids removed over volume of gas, which is equal to volume of cake over volume of gas processed. Vs, again, is equal to Q over A equals 1 over A dV by dt equals to P1 minus P3 mu VW over Ka plus alpha, and alpha is the resistance of the filter media. That will lead to B over A squared equal to mu W over 2K plus B over A mu alpha, which is also equal to P1 minus P3 times T. So let's use this equations and apply it in an exercise. A bag house has 6 compartments, each with 112 bags that are 8-inch in diameter and 22 feet long, for an active area of 46 feet square per bag. The gas being cleaned has a flow rate of 86,240 feet cube per minute. Pressure drop through a freshly cleaned bag house is estimated to be 0.5 H2O. The bags are operated until the pressure drop is 3-inch water, at which time they are taken out of service and cleaned. The cleaning frequency is once per hour. The incoming gas has a particle loading of 13 grains per feet cube. The collection efficiency is 99%, and the filter cake is estimated to be 50% solids, with the balance being voids. Estimate how thick the cake is when the bags are taken out of service for cleaning. What is the permeability K of the cake? So we'll start with Vs is equal to Q over A, which is Q, as given here, is 86,240 feet cube per minute over the area, which is 5 times 112 times 46. 5 is used here because one of the 6 compartments is always out of service for cleaning. And remember, they are 6. However, in operation, you have actually 5 at any time. So that's why we have the 5 over here. Now, the 112 are the number of bags, and 46 here is the active area of each one of them in feet square. So this will give you 3.35 feet per minute, is also equal to 1.02 meter per minute. Vs is commonly referred to as the air to cloth ratio or phase velocity. So air to cloth ratio, this is this Vs. If the filter remains in service for 1 hour before cleaning and Vs is constant, then 1 square foot of bag will collect the following mass of particles. M over A is equal to C Vs eta T, so which is coming as 13 times 3.35, which we just calculated, times 0.99, because that's the efficiency. Efficiency that we talked about, times 60, and that's for per feet square, pound mass per feet squared equals to 1.8 kilogram per meter square. The thickness, M over A over rho, is equal to 0.369 pound mass over feet square over 2 gram per centimeter cube times 0.5 times 62.4 pound mass centimeter cube per feet cube. That's also for conversion of units. That's equal to 5.9 times 10 to the power negative 3 foot, which is equal to 0.071 inch, again equivalent to 1.8 millimeter in diameter. If alpha is equal to 0, we can say that K is equal to Vs delta X mu over negative delta P. Now we know the Vs, we know we can convert 0.071 foot to inch. We multiply by 0.018 centipoise times 2.09 times 10 to the power negative 5 pound force, and we divide by 60 minutes for conversion over 3 inch that was given here. That's the pressure drop. And times 5.202 pound force per feet square in water. That's equal to 7.96 times 10 to the power negative 12 feet square, which is also equal to 7.4 times 10 to the power negative 13 meters square. So in the next, we'll talk about depth filters in just a minute.